Hello everyone. My name is Fernando Gontijo. I am a PhD student and researcher at Unicamp working under the supervision of Professor Paulo Caggiari. Today we present our work titled on the use of Gumbel-Softmax for differentiable QAM semantic communication. This research explores how we can integrate pattern language models and transformers with communication systems using Gumbel-Softmax tricks to enable differentiable modulation. Our goal is to make semantic communication system trainable end-to-end. Thank you all for your attention, and let's begin. This first slide is just for motivation. So you can say that in traditional system, are built strictly on channels classical framework. So they apply source coding and channel coding independently and treat every bit as equally important. So classical systems are unable to exploit the semantic redundancy, so they may waste channel resources with information that is not essentially understanding. The semantic communication introduces a different paradigm. Instead of ensuring that every bit is perfectly recovered, the goal is to reconstruct the intended meaning of the message. This opens the door to more robust and efficient communication in noise embedded limited scenarios. Just two examples to illustrate. Technically, these sentences are different, but semantically they are identical. Semantic communication system will check them equivalent because both convey with the same meaning. For the system description, the architecture of the system we provide in this work. The system begins with a semantic encoder, which receives the input sentence. First, the encoder extracts the high-level semantic features using pattern language model or transformer layer. Then a second model is a fully connected layer, does the channel encoder step. After this step, the signal goes through the QAM modulation block that applies the Gumbel-Softmax trick. The modulated signal is transmitted through the veiling channel, and the receiver they apply the inverse of the operations. And similar, the model allows end-to-end optimization from semantic to modulation and coding, making the entire system joinable, trainable. Just an example how to map the semantic features to QAM symbols. After the semantic encoder, the channel encoder will produce a vector of logics. We convert these logics into one-hot representation, and then the one-hot vector selects exactly one entry from the constellation matrix. This operation is equivalent to performing a lookup in QAM modulation, but writing in a matrix multiplication. It fits naturally inside a neural network pipeline. The main challenge is that this discrete selection is not differentiable, so meaning gradients cannot pass through. This is the motivation to use the Gumbel-Softmax trick. Before the explanation of the Gumbel-Softmax trick, we have to explain the Gumbel-Max trick. This selection is typically done using the Gumbel-Soft trick to select the points in the one-hot representation. The idea here is to draw a sample for the categorical distribution. The Gumbel distribution models stream events and provide the type of random noise that, when added to the model logics, allows us to compute the samples. This expression gives us a valid categorical sample that selects exactly one constellation index without explicitly sampling from the discrete distribution. But it's not differentiable because of the Argmax operation, so we have to reflect that using the Gumbel-Softmax trick. So the Gumbel-Softmax trick is a differentiable extension of the Gumbel-Max tricks. So instead of returning the only Argmax index, it produces a soft one-hot vector using the Softmax function. This creates a continuous approximation of the categorical samples process. So with this illustration, we can multiply the soft samples with the constellation matrix to obtain a differentiable estimate and modulation points. It allows the gradient to flow the entire process into the training ancient system. The training procedure used here are not different from the other training procedures. The first step is initialize the models, parameters, the input token, and then pass it through the semantic encoder and channel encoder. And then we use the Gumbel-Softmax trick to have the samples and multiply that with the constellation matrix to produce the transmitted symbols, which is then sent to the channel. At the receiver, apply the inverse the decoder of the encoder steps, and we compare the output with the original input using Corral's entropy loss. So during the training, gradient flows through all components because of the Gumbel-Softmax trick. So this enables joint optimization of the semantic encoder, channel encoder, semantic encoder, and channel decoder. The metrics used here are two, the blue score and the bad score. The blue score measures surface level similarity, but does not capture deeper semantic meaning. But the bad score uses contextual embeddings from the pretended bad model. This bad score much more aligned with semantic communication since it reflects the meaning. The models and the data sets we use here, the model are three. We use three models to compare the results. The first one is not a semantic system. One is a Huffman plus Turbo system. The second one is a base model using transformers models and fully connected layers to channel encoding and this Gumbel-Softmax QAM. The second one uses the 5 small models for semantic decoding and encoding. The training and the test was used, applied the Europol dataset that has 2 million sentences and 53 million words. For the blue results, the proposed semantic system Signal Power performed the classical ones. The 5-based models show superior performance in medium to high scenario conditions, while the base model demonstrates good results. When I apply the modulation, the low order modulation, 16 QAM, 45, and the 5 model, and the base model performance drop. But when we apply the high order modulation, the base model achieves the best blue results. The base model and the 5 base model, so since the large constellation possesses more semantic information during the mapping. The same is known for the bad score. Here the results for models with Gumbel-Softmax trees are not different from the blue one. Results for 16 QAM model are worse, but is better for 256 QAM. Overall, both performance indicate that semantically aware encoding is more resilient to chaining environments, and the Gumbel-Softmax approach enables stable differential QAM mapping during training. So to summarize the results, we have when you move to 16 QAM, the performance drop, but when you use the 256 QAM, results in a loss. This loss information results better scores. Finally, because of the Gumbel-Softmax tricks, the entire system can be trained end-to-end, which contributes to the overall performance gains. This results reinforce that semantic communication combines the differentiable QAM multiplication, provides a more noise resilient and efficient alternatives. For future works, we want to use larger models in the semantic code encoding process, like the 5-base and batch-base. You want to use learnable and data constellations and other data set for training, for testing, different from the training one. So, I want to thank you all for the attention. It was a very fast presentation. We tried to explore the Gumbel-Softmax trick. And I'm open for questions. I'll be very happy to have questions or comments and suggestions. Here's my email, and thank you again.